So we move to the second talk by Don Kurtz, University of Central Lancashire, the title Asteroseismology, a New Keplerian Revolution.
Thank you, John, and good afternoon, everyone. 50 years ago, this semester, I was a first-year undergraduate at university studying oceanography and marine biology. But out of interest, I took a class in astronomy from a very charismatic teacher. He and I have remained lifelong friends. It obviously affected me, and I changed fields. And I began avidly reading astronomy, and at that time, one of the books I bought was out of this old Dover reprint series, The Internal Constitution of the Stars by this society's 42nd president, Arthur Eddington. That book was already 40 years old at that time. Now, Eddington starts that book with these words. He says, "At first sight, it would seem the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. Our telescopes may probe farther and farther into the depths of space, but how can we ever obtain certain knowledge of that which lies behind substantial barriers? What appliance can pierce through the outer layers of a star and test the conditions within?" Eddington had a good answer to that question. We know what stars look like on the outside, and with theory, we can calculate the inside. And that's what the book's about. It's about the theory of stellar structure. But he warns on that first page also, we would be unwise to trust scientific inference very far when it becomes divorced from the opportunity for observation. He didn't see directly that it was coming, but we would find the time when we could look inside the stars and see inside. And that time's come. The field's called Asteroseismology. It began to arise just as I was an undergraduate 50 years ago, reading Eddington's book, and led me through the years eventually, as you can see, to be one of the co-authors on the fundamental textbook in the field. The thing that has revolutionized our work has been the Kepler mission. Now, you know the Kepler mission because of its discovery of nearly 5,000 planets or planet candidates around other stars. It has also revolutionized stellar astronomy, and that stellar astronomy feeds directly into the planet studies, but of course it's of interest to those of us who work on stars independently. When I was a young postdoc in South Africa, I was doing some of the most precise measurements of stars of anybody on the planet. I was measuring stars to a precision of a part in 10,000. I would observe one star all night when it was dark, when I had the telescope, when the weather was clear. You can imagine what the data sets looked like. Kepler, there's one light curve from the Kepler data set, just one. I'll explain what that squash is in a moment. It is 4 years long and nearly continuous, and it has a precision for the brighter stars of a part per million. 200,000 stars observed that way. Everything we look at's a new discovery. If I just take you into that same light curve over just a few days, you'll see a lot of variability there, and I have to tell you that the precision of the data points is about 1/50th the size of the data point. Every single bit of variability you see in that light curve is real. So let's look and see how we can use that to learn about the insides of the stars. Stars are spherical. When they're pulsating, the wave equation for the star, the solutions to that wave equation are spherical harmonics. You learned spherical harmonics in quantum mechanics when you were undergraduates, if you did such things. And what we need for today are the quantum numbers that describe the pulsations. The number of radial nodes, the number of surface nodes, which can either be lines of latitude and longitude, and the number of those that are lines of longitude. Now, we can have a graphical view of that. For stars that are radially pulsating, which is what you know for Cepheid variables or our Lyrae variables, the star swells and contracts spherically symmetrically. It gets bigger and smaller, hotter and cooler, which is being represented by the color changes there, and as a consequence, brighter and dimmer, and that's actually what we're observing with the telescope, is the brightness change. Star pulsating in a radial mode like that is in many ways equivalent to an organ pipe, and just in a one-dimensional view of an organ pipe, the bottom of the pipe is a node, the surface is an antinode, and that's true for the star too. But notice that in an organ pipe, in an oboe, in a bassoon, the first harmonic, the first overtone, has a node 2/3 of the way along the tube, And the ratio of that first harmonic to fundamental in period is 0.33. For a Cepheid variable, that number is 0.7. The reason? The Cepheid variable is centrally condensed. And as soon as we've measured 2 pulsation frequencies, we just got to look inside the star to see what the interior structure is like. That's a first constraint. I'll take you much further as we go along. Let's look at what the non-radial modes look like. The simplest non-radial modes are dipole modes. The central one right here is what we call the axisymmetric or zonal dipole mode. The equator is a node, and as the star pulsates, it appears to move up and down in space. The North Pole swells, the South Pole contracts. You'll see the color change. The color change is a temperature change. The star gets brighter and dimmer. On the other hand, if we have sectoral modes, where m is equal to L, we end up with modes that rotate. That's due to this phase factor up here mixing with the time variation. The importance of this here, we're going to come back to this. For a perfectly spherical star, all 3 of these modes would have the same frequency. But as soon as the star rotates, Coriolis force lifts the degeneracy of those frequencies in the star's frame, and from the observer's point of view, the mode going with rotation has a higher frequency due to the rotation, the mode going against it a lower frequency, and by observing those 3 frequencies for a set of dipole modes, we now have got a measure of rotation in the star. And we'll come back to that with some impact in just a little while. One more set just to give you the idea. Quadrupole modes have got 2 nodes on the surface. They're lines of latitude for a zonal mode. The star looks like this. This is exaggerated in amplitude, but correct in terms of the kind of distortion. The tesseral mode has 1 line of latitude and 1 of longitude. It rotates, and there's another one going the other direction over here that I didn't put in the diagram. There are 5 of these. And the sectoral mode would look like that. Again, we're going to use this in a little while to look at some novel rotation in stars. How does astroseismology work? What's the fundamental principle? Well, so far I'm talking to you about acoustic waves, pressure waves in the star. This is a cross-section of a star. There's its surface. This is the center. The pressure wave is a sound wave. The sound speed depends on pressure over density, sound speed squared does, or temperature over mean molecular weight. And for a radial mode, it'll travel right to the center of the star and back out again. But the non-radial modes are not aimed at the center, and of course, with a temperature gradient, there's a sound speed gradient. The lower in the star the wave is, the faster it travels, so it's refracted back to the surface. It can't escape, and it bounces around inside what we call the acoustic cavity. Modes with many, many nodes on the surface, these are high L modes, only sample a layer near the surface of the star. Modes with fewer nodes penetrate more deeply. In the case of the sun, we can see about 2 million independent pulsation frequencies, and that maps out the sound speed inside the sun, the square of the sound speed, to a precision no worse than 3 parts in 1,000 throughout the entire sun. When somebody tells you the core temperature of the sun is 15.4 million Kelvin, that the core density is 155 grams per cubic centimeter, or argues about neutrino production inside the sun, that's not theoretical, that's observed. We can see the core of the sun. There are 2 kinds of modes. Besides the pressure mode, there's also something we call a gravity mode. The gravity mode is actually a buoyancy restoring force for the mode. Although we call it gravity, buoyancy restores the mode. And for the pressure modes, they're largely trapped in the outer part of the star. For the gravity modes, they largely sample the core, and that's very interesting. There is a way to reach right into the heart of the star and look what happens where all the action is. Now, this happens to be a ray diagram for the sun, and you'll notice the G modes don't reach the surface. That's because with buoyancy as the restoring force, when you get to a convection zone, the buoyancy is runaway. That's what convection is, and there's no standing wave solution. So for the sun, we would argue that we've never seen G modes in the sun. A few of my observing colleagues claim to have seen them. The rest of the community doesn't believe them. We would love to see them. We've been trying for 40 or 50 years to see G modes in the sun because they will tell us so much about what's happening in the core. I'll come back to that in a moment. We've not succeeded for the sun, but we have succeeded elsewhere. Why do the stars have oscillations? There are 2 main driving mechanisms. One of them is a heat engine mechanism. Energy coming out from the star, as in a Cepheid, is absorbed by a gas in an ionization zone, typically hydrogen, helium, sometimes iron when it's very abundant. The additional energy in the gas causes the star to swell, but the ionization of the gas drops the opacity. Radiation flows through, the outer layers way down on the star, it recollapses, and on recollapsing, you get recombination and the opacity goes back up. What you get is you get heat gain on compression, and that's a heat engine. That's what drives the common oscillators you may be familiar with, Cepheids, RLIRE stars, and so on. For stars like the Sun, the solar-like oscillators, the red giants, they're simply resonating in a very noisy environment. The Sun is incredibly noisy. Now, you know that it's got storms, it's got magnetic reconnection, it's got flares, it's got coronal mass ejections. The main source of noise in the Sun is convection, and it's in the granules, and it's largely from the downflowing sheets of gas in the granules that produce a background noise that set the whole Sun to oscillating. This is the space that I live in as an astroseismologist. This is frequency space. It's a Fourier Transform of data from the Birmingham Solar Oscillation Network. They've got 6 telescopes around the world. And this Fourier Transform is for data that stretches for decades on the Sun. This is one of the most exquisitely precise physics experiments ever done. I'll make that point more carefully in just a moment. First of all, the scale. This frequency scale is probably unfamiliar in microhertz. So 3,000 microhertz here is a period of 5 minutes. The Sun's oscillations range from about 2 minutes to 5 minutes, and you'll see that there's a comb of roughly equally spaced frequencies. Let's look at the scale on the other side. This is in radial velocity in a spectral line. There's 1 centimeter per second. That peak right there represents the surface of the Sun. Now, 5 minutes, 300 seconds, the surface of the Sun comes up roughly for 150 seconds at 1 centimeter per second. It lifts by 1.5 meters, it drops by 1.5 meters. For some of these smaller peaks down here, you're watching the line-forming region in the surface of the Sun move up and down by about 10 centimeters for a 700,000 kilometer radius. What do I mean by the radius of the Sun? I don't know. Good question. But I don't actually care, because whatever it is, I can get the frequencies, and that's what we use to look inside the star. Let's look at that comb in a little bit more detail. We're going to look at that comb in a little bit more detail to see how we use it to get fundamental data on the stars, primarily for feeding into the planetary studies with exoplanets. So these are space data, again for the Sun, and what you're seeing is that there's a basic large separation, which is an inverse of the sound travel time from the surface to the core and back out again. And you'll see that there are various modes. These are the radial overtones. This is a radial, sorry, these are the radial nodes. This is a radial mode, this is a quadrupole mode, that's a dipole mode. We've got this basic large separation and small separation. This depends on the structure of the whole star. This depends largely on the conditions in the very core. And if I skip to just 3 out of tens of thousands of stars that we can now do this for, if we look at various stars near the main sequence, this is now 2400 microhertz, a little bit lower frequency than the Sun, 1900, 900, we're moving up to giant stars. The peak where the star oscillates moves, we call that nu max, the place where we get the maximum amplitude for frequency, and nu max is proportional to the surface gravity, mass over radius squared. The large separation is proportional to the square root of density, or square root of mass over radius cubed. We can then take those two and extract mass and radius. Now, if you're doing exoplanets, you watch a transit of an exoplanet, and what you see is you see the planet block out some light from the star. That tells you the radius of the planet if you know the radius of the star. You then get a big telescope on the ground, and using spectra, you do radial velocities. Using the original Kepler, not the telescope, Kepler's third law, you get the mass of the planet if you know the mass of the star. How do you know those two things? You know the mass of the star and the radius of the star from this. And we can feed that back now for thousands of stars. Mass and radius for single stars. We can also do age. The mass and radius are largely model independent. Highest precision we're reaching in comparison with Alpha Centauri, where we can look at the binary numbers, we're hitting precisions of 2 or 3%. In general, better than 20%. In the case of ages, they are model dependent, just as they are if you use isochrones for clusters, but now you don't need clusters. You can do this for just one star. So this is a plot of that small separation versus large separation from the main sequence for different masses, and then along the evolutionary tracks in this diagram to the terminal age main sequence, we can actually give you an age for the star while it's on the main sequence. Now, for galactic archaeology, what used to be galactic chemical evolution, we would like to do this largely for red giants because you can see them at great distance, and you'll see the red giants in this diagram, everything becomes degenerate. But there are other ways. The red giants pulsate in these gravity modes, and if we look at the periods of the gravity modes and the separation in the periods, we call that delta P, versus the frequency of the oscillation, the stars that are burning helium in their core and are convective are a completely different place in the diagram to the ones that are hydrogen shell burning, that are on the red giant branch for the first time. In the HR diagram, you cannot separate these stars. In this diagram, you can. We can tell you the age also of the red giants. And so if you're doing galactic archaeology and trying to map out how the chemical evolution of the galaxy changes, you need to get spectra for all these stars, but we'll give you mass, we'll give you radius, and we'll give you an estimate of the age. So there's the industrial use of astroseismology. Now let's look at some of the specialist uses that in fact are of much greater interest to me and to those of us who work in the field. There's a cross-section of the sun in diagram. Here's the surface. This is the rotational axis. This is the equator. And as you know, we've known for centuries, the equator of the sun rotates with a period of about 25 days. The pole rotates with a period of 35 days. Now, when I was a student, that 50 years ago in San Diego, the model for rotation in the sun was that it rotated on cylinders. And if you were at a certain distance from the rotation axis, everywhere would be 35 days. We can now look inside the sun with those rotational modes I showed you, and the story's very different. You can think of the sun, if you like, as having a rotation period of 27 days with strong easterly winds blowing at the equator and strong westerly winds blowing up at the poles, and we never could have seen that before helioseismology. Now back to those gravity modes and trying to see into the core of the star, trying to look at rotation. For stars, internal angular momentum transport over their evolution matters a lot, but it has been until just recently a purely theoretical field. It is no longer purely theoretical. Just a couple years ago, my colleagues and I, for the first time, measured rotation right from the core of a hydrogen-burning star to the surface. How did we do that? Back in a Fourier Transform. This is down in the G mode region. This is now the frequencies and cycles per day, so this is a period a little bit less than a day. The amplitude's now in millimags or parts per thousand. You can see pairs of frequencies, and those pairs are those rotational dipoles. One's going this way, and one's going that way. And the difference between them measures the rotation of the core of the star. There's the equation that describes it. It depends on a constant we call the Ladue Constant. It depends on a function that samples how the star reacts, how the frequency of the pulsation reacts to the structure of the star and the rotation of the star. We could derive model independently that the core of that star has a rotation period greater than 105 days. It's very slow for such a hot star. The star has a temperature of about 7,400 Kelvin. How do we do that? Well, here's that kernel, that function I just showed you, scaled to the radius. This is fractional radius of the star. The G modes are sampling the inner 20% of the star or so. The pressure modes are sampling the outside, and they also show rotational splitting. There's a dipole with its 3 modes split. There's a quadrupole with all 5 modes split. And now we can measure the rotation of the surface. Same equation applies, except now the Ladue constant is a number that's very close to 0, and we get a maximum rotation of the surface of 98.57 days. This star is nearly rigidly rotating. That's a surprise. And its surface is rotating faster than its core. How did that happen? If you think of a star evolving as it forms and collapses down the Hayashi track, it's completely convective. It's born as a rigid rotator. And then as it evolves, the atmosphere swells up and slows down. The core contracts and speeds up. And so obviously there's an angular momentum transport mechanism to transfer angular momentum from the center out. What mechanism transfers so much angular momentum it actually spins up the surface? We've got ideas on that. We're working on it. The point to you is this is a brand new field observationally. It was purely theoretical until just a couple years ago. We can now measure rotation inside stars, hydrogen burning on the main sequence, red giants, white dwarfs, and we're looking at how the angular momentum transports through the star throughout its lifetime. And I'll repeat that, we're looking at it, we can see it. This is not something just calculated. Going back to that P-mode quintuplet I just showed you, what I didn't tell you earlier is that these outer two modes, these were the ones rotating sectorially, sample the star in latitude differently to the tesseract modes. And so by looking at the splitting of these frequencies, we can get a measure of the shape of the star. And that led to a remarkable result we published last year in Science Advances. We measured the shape of the star, and it hit the newspapers, about 500 newspapers around the world, with the headline that we had discovered the roundest object in the universe. We showed that that star's equatorial radius is only 3 plus or minus 1 kilometer bigger than the polar radius. And that was a surprise, because even with that slow rotation, it should be more oblate. And so how do we explain that it's not more oblate? Well, the first thing we reach for is magnetic field. And we're waving our hands at the moment trying to figure that out. Now, a few years ago, I was interviewed by a journalist for the Science News magazine about strange stars Kepler's discovering. And I want to show you just a few of those strange stars to wrap up here. These are of great interest to those of us who work in the field because they're interesting new puzzles. They may not be the astrophysically most important. We have to discover that yet. But let me show you one of the first ones we discovered. We discovered the heartbeat stars. And this one, Kepler Object of Interest 54, was the first one we picked up. This light curve is 6 months long. 6 months of continuous data, amazing. It's actually 4 years, I'm only showing you a bit. And every 42 days, the star goes blip, 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 by 7 millimags. From the ground, you'd hardly see it. We looked at that and thought, well, what is that? It kind of looks like an electrocardiogram, so we called it a heartbeat star. And then when we fold on the 42-day period, notice it's wobbling, and the wobbles always end up on exactly the same place. So the wobbles are somehow coupled to the period of the blips. It didn't take too long to figure it out. Here's an animation from Jim Fuller we work with. Jim is a postdoc at Caltech and Kavli Institute. That star is one of the most eccentric binaries known. Eccentricity is around 0.9. And when the two stars pass at periastron, they almost touch. And as they pass at periastron, they stretch each other out of shape. That's what gives you the blip. And that sets them to wobbling in tidally excited oscillations, for which we've had theory for decades, but never before observations. We've got almost 200 of these objects. And I'm very pleased to tell you that I had a student finish her PhD last December, Kelly Hamilton. She did her undergraduate astronomy when these stars weren't known to exist, and she did her PhD leading international teams in a field that didn't even exist when she took her first astronomy course. She's now at Villanova University in the United States. Hiramoto Shibahashi and the University of Tokyo and I have worked together for decades, and working on these stars, we realized stars can be good clocks. Now, you know that. Binary pulsars, you can do exquisite timing, but many pulsators are very good clocks. And so we don't actually have to go to the telescope and take spectra and measure the frequency shift in the spectral lines of stars. We can measure the frequency shift in their pulsations and solve binary star orbits absolutely completely, as has been done traditionally using spectra. The first technique we called the frequency modulation technique. The solution is that in the frequency spectrum, you end up with a series of Bessel functions. You just get a whole multiplet. And from that, you can extract everything you want to know about a binary orbit. This can be automated using what we call phase modulation. This is being led by my previous student, Simon Murphy, who's now a postdoc in Sydney with Tim Betting. And this is the time delay in two stars that are oscillating as they come towards you and move away from you. And it's exactly equivalent to a radial velocity curve in a double-line spectroscopic binary. We call this a PB2 system, pulsing binary, where you can see both of them. And that can be solved for all of the elements of the orbits of both objects. Where has it led to? Well, Simon led a discovery just recently of a planet orbiting an A star. There's no other way to find planets around A stars. Transits don't work, the A stars are too bright. Radial velocity technique doesn't work, the A stars are too massive. So we're pushing down into the realm of finding planets around pulsating stars. Now, some astronomers worked on binary stars their entire career. I can think of one, Donald, that you perhaps know. Hundreds of stars over a whole lifetime. Simon has just done complete orbits for hundreds and hundreds of stars in 2 years since his PhD. with this incredible Kepler data set. Now, the last thing I want to point out in the data set, fun for us, there's a box I call the what is it stars. There are lots of them. I'm only going to give you 2 examples. Here's one where I just pulled out a few days, and every 3.5 days, this thing does something repetitive. Something. I don't know what that repetitive thing is. All right, you can throw out spots if you like, but that's a lousy hypothesis because you can make anything with spots, just the more you've got, the more you get. I don't know what that star is doing, and I've got many of them like it. It's a what is it star. The one that hit the news most is Tabi Star. 2 years ago in the press, it was announced that there was a disintegrating Dyson sphere around the star from an alien civilization. Well, that was pretty wild, but here's what the data look like. This is out of data that are sitting on this computer I'm working on right here. Here's 20, 40, 60, here's 90 days worth of data. This is in flux. And so notice that things are passing in front of this star, and things as big as stars are dropping the light by 20%, but not periodically. What is blocking the light from this star? It's not periodic. Next guess, oh, giant comets? Well, maybe. So I find these what is it stars to be great fun. The industrial part of astroseismology is what we feed into the planet searches and the galactic archaeology. The important part in terms of the astrophysics for stars is internal rotation and internal structure for the stars. If we go back to Eddington's question, what appliance can pierce through the outer layers of a star and test the conditions within? Well, I've just answered that for you. It is, of course, astroseismology. And I call it a new Keplerian revolution because that Kepler data set has completely revolutionized the study of these stars, and there is no other mission coming that's going to replace that data set. That 4 years of continuous data will be unique for some time to come. I went through this pretty quickly. If you would like to follow up on this more at a more leisurely pace, Connie Arts, Simon Jeffrey, and I published something on it in the House Journal, A&G, last year, and you can look at the paper of this talk, if you like, by going back to that issue. Thanks for your attention this afternoon.
Thank you very much, Don. You said there's nothing planned after Kepler, is that correct?
I've given you the misimpression, John. There are missions planned. TESS is coming.
Yes.
The Transiting Exoplanet Survey Satellite, and it will do first the entire southern hemisphere and then the entire northern hemisphere for 1 year each. But each field will be about 27 days, with some stars observed for 1 year. Nothing will be observed for 4 years. The Plato mission to go up in 2023 may have a lifetime beyond its 4-year nominal lifetime, and then we could get a data set bigger than Kepler, maybe even 6 years worth of data, taking us to 2030. You might understand why, from my point of view, that might be the same as never.
Okay, time for one question. Yes, Peter.
Thank you for a really interesting talk. You made the point that in a star like the Sun that we don't see the G modes because they don't get to the surface. But is there any coupling between the P modes and the G modes?
The question is there coupling between P modes and G modes? We can't see that in the Sun, but we see it in abundance in main sequence stars a little further up. The one that I showed you, the internal rotation, I can see the P modes and G modes coupled quite easily. And in the red giants, it's dominant. We get what we call mixed modes, which have got the character of both. So the answer is yes, they definitely do couple.
Okay, we must move on, I'm
Okay,
afraid. Thank you
you.
very much indeed, Don.